Welcome back to the series on statistics. In this video, we're going to derive the exponential distribution. And this is going to model the distribution for the amount of time to the first occurrence of some event, whatever you're modeling, when the average number of events over the course of the time interval is known. So for example, if you know that you receive, on average, 10 phone calls between 2 and 3 p.m. on some workday, we can model the distribution of the amount of time you have to wait until your first phone call starting at 2 p.m. with the exponential distribution. And so that's going to be the goal in this video. You might think that that sounds similar to the Poisson distribution, which is modeling the number of occurrences of some event when the average number of events over the course of that time interval is known. And indeed, the Poisson distribution and the exponential distribution are highly connected. However, given that the Poisson distribution is going to be modeling occurrences, numbers of occurrences, that's a discrete probability distribution. But this exponential distribution, this is modeling the amount of time to the first occurrence, so this is going to be a continuous distribution. So there's uncountably infinite many possibilities for the amount of time to the first occurrence of some event. And so this is going to be dealing with uncountably infinite outcomes. This is a continuous probability distribution. And so that's the key difference here. This is going to give us some practice both in deriving continuous distributions and also giving us a chance to discuss what a random variable is in the context of a random variable with a continuous probability distribution. All right, so without further ado, let's get started. This distribution's derivation is going to proceed very similarly to the Poisson distribution. Essentially, we have this time interval here, and we want to model this time interval as a binomial distribution. We know how to work with the binomial distribution. We have a PMF for the binomial distribution. We have a CDF. We have all of those attributes. So if we can model this as a binomial distribution, then we can essentially derive the probability density function for the exponential distribution, or the cumulative distribution function for the exponential distribution, and then we'll have all the information to completely characterize this distribution. And so, if you recall, we had to make some assumptions to derive the Poisson distribution. We're going to have to make many of those same assumptions. All of these assumptions just allow us to essentially model this as a binomial distribution. We have to make the assumption that events are independent, so that there's an equal likelihood of the event occurring at any point in this subinterval. That's our second assumption. Technically, we need both of these because if we have an equal likelihood at any point throughout the time interval, but they're not independent, then you could imagine that the probability, if one event occurs and it might influence the probability of other events occurring, then we're no longer able to model this as a binomial distribution. And so we have to meet both these criteria, and we also have to meet this third criterion here, which says that events cannot occur simultaneously. And essentially, just like when we derived the Poisson distribution, our goal here is to chop up this time interval into several different equally sized subintervals. And then we want to say, okay, what's the probability of the event occurring in this subinterval? And what's the probability that it does not occur in the subinterval? And you can imagine that as we chop up these intervals, maybe this rate parameter is like 36, for example. And that's the amount that you would expect to occur over this entire time interval here. And we chopped it up into 4 segments. We're also assuming that events have an equal likelihood of occurring at any point throughout the time interval, which means that this rate parameter is going to be linearly dependent on the length of the interval. Or in other words, if we're expecting 36 events to occur over the length of the entire interval, and this is 1/4 of the interval, then the rate parameter here, just for this little section, this subinterval, this will be equal to 9. And so we would be expecting there to be 9 events that would occur in this subinterval. And so if we're expecting 9 events to occur in this subinterval, then you can imagine there's a probability that no events occur, there's a probability that 1 event occurs, there's a probability that 2, that 3, that 4, that 9, that 10, all these different possibilities of different numbers of events that can occur in any one of these subintervals. This isn't good. This is essentially our starting point. But you can imagine that as we make these subintervals smaller and smaller and smaller and smaller and smaller, the probability of there being more than one event that occurs in any one of these subintervals, we can sort of put a limit on that. And if we were to take the limit as the number of subintervals goes to infinity, for example, then the probability of there being more than one event that occurs in any one of these given subintervals is going to go to 0, because we're making this third assumption that events cannot occur simultaneously. And the probability of there being more than if the probability of there being more than one event goes to 0, and the probability of there being one event maybe that also goes to 0, but we can sort of work with that mathematically. Then we can model each one of these subintervals as a Bernoulli trial, where there's only two possibilities, either the possibility that the event does not occur or the possibility that it does occur. If we are able to make these subintervals small enough, we don't have to worry about this possibility of there being more than one event that occur, as long as we make this third assumption. So that's our goal, is to break this up into several different subintervals, and then as we break it up into smaller and smaller subintervals, eventually we're going to take the limit as the number of subintervals goes into 0 and the length of the subintervals becomes infinitesimal. Then we're going to start to be able to make statements about this distribution. And so that's the goal here. All right, so let's say that n, we'll call this the number of subintervals. The number of subintervals. And I do want to make one more assumption here, which is just that the length of the interval here is equal to 1. Now, you might think that that's a big assumption, but it's really not. We could just scale this rate parameter to be whatever it needs to be equal to make this true. And so, for example, if we know that we're expecting 20 different events to occur in 3 hours, we could just scale that to be 20 divided by 3 events that we are expecting to occur in 1 hour. And we can do that because we're making the second assumption here, that events have an equal likelihood of occurring at any point throughout the time interval. And so we can model every situation we could model with a time interval of variable length just by scaling this rate parameter accordingly. And so I'm going to make these two assumptions, or this assumption here, and then I'm going to, without loss of generality, and then I'm going to set n to be the number of subintervals. And now if we're modeling this as a binomial distribution, then we want that the mean of the binomial distribution, the expected value of the binomial distribution, the expected number of events that occur in all these different trials, we would want this to be equal to the rate parameter, because we know that that's the expected number of events that occurs over this time interval. And so if this number of different subintervals, or the number of Bernoulli trials, multiplied by the probability of success in each trial, is equal to the mean of a binomial distribution, and we're using a binomial distribution to model this situation, we want the mean of that binomial distribution that we're using as a model to agree with the expected number of events, or the expected value that is known in this situation. Now here this is going to be an approximation, since we're just approximating this as a binomial distribution. But if we take the limit as the number of these subintervals goes to infinity, then this is going to cease to be an approximation and is going to become an exact, it's going to become equal to lambda here. And so we're ultimately that's what we're going to do, but essentially right now I'm just going to make this statement that the probability of a event occurring in any one of these subintervals, we can now solve for this from this relation, and this is going to be approximately equal to lambda over n. All right, so now if we want to solve for the exponential distribution, if we want to find out its cumulative density function, I claim we can already kind of figure it out just based off of this information alone. And so if we let t be an exponentially distributed random variable with a rate parameter of lambda, or in other words, the time to the first occurrence of an event, when a known constant number of events in some interval is known, that's our rate parameter here, then we want to solve for the probability that that random variable is less than or equal to, here I'm using little t, just to indicate some time value here along the interval. And so if we're breaking this up into essentially infinitely many subintervals, you can imagine all these different subintervals here. And then what if we wanted to solve for this probability? Well, this is going to be equal to the probability that the event occurs in this first interval, plus the second, plus the third, plus the fourth, all the way up to the last time interval that includes this value t here. And if we wanted to sum up all these different probabilities, we don't really have to worry about summing up these, or if we want to sum up all these different probabilities, we could just sum them up, because all of these are mutually exclusive. In other words, the probability that an event occurs in, the first occurrence of an event is 1.5 seconds, and the first occurrence of an event is 2 seconds, or takes 2 seconds, the probability of that is 0. And so, because these are all disjoint possibilities, we could just add up all of these different possibilities. And so what's the probability that the event occurs in this first subinterval here? Well, we just determined an approximation here, that the probability of the event occurring any one of these subintervals is going to be approximately lambda over n, but this is going to cease to be an estimation as we take the limit as n goes to infinity. And so the probability of an event occurring in the first subinterval, that's just lambda over n. Okay, so that's our first possibility. And what about the probability of the event occurring in the second subinterval? Well, in order for that to occur, the event couldn't have occurred in the first subinterval, and so we'll have 1 minus lambda over n. That's the probability of the event not occurring. And then we want to multiply by the probability that it does occur in the second subinterval. And so this is the probability of it not occurring in the first times the probability it does occur in the second. So this total expression here is going to give us the probability of the event, the first occurrence of the event being that second subinterval. And then if we wanted to find the probability of the event occurring in the third subinterval, this is just going to be the probability of the event not occurring in the first subinterval times the probability of the event not occurring in the second subinterval times the probability of the event occurring in the third subinterval. And in total, this whole expression is going to give us the probability of the third subinterval being the first occurrence of the event. And so if we keep doing this, the pattern here should be clear. We're just going to add a little exponent here. We can add some k here. And so this is the probability of the event not occurring in the first k subintervals, and then the probability that the event does occur in the k plus 1th subinterval, for instance. And if we sum up over all of these possibilities, and we start summing from 0, then this is if we start where k is equal to 0, then this is going to go to 1, and this is just the probability of it occurring in the first subinterval. Then when k is equal to 1, this gives us the probability of it occurring in the second subinterval. And so we want to do this all the way until the last possible subinterval. And so the only thing left here is to figure out what's the upper bound on this summation. And if we want to know what the upper bound of the summation is, we just want to know what the last, or how many subintervals there are contained between 0 and this time t here. And I claim that if we know the number of subintervals is n, then we know that the width of each one of these subintervals, we'll just take the width of the total interval here, t, which we said is equal to 1, and we'll divide it by the number of subintervals to get the width of a subinterval. And so the width of a subinterval is going to be equal to the width of the total interval divided by the number of subintervals. And then if we want to know how many subintervals are contained in this interval from 0 to t, then we just need to take t and divide it by the width of the subinterval. And so this is going to tell us that there's tn subintervals contained in this interval here. And so if we want to find the last subinterval where this event is true, this is an event, the event that the time to the first occurrence of the event is less than or equal to t, we want the last subinterval to be equal to the last subinterval in this interval here. And so we need to sum from k is equal to 0 to tn minus 1, and we need to be careful here and sum all the way to tn minus 1, because if we plug in tn minus 1 here for k, then the last value in the summation is going to be 1 minus lambda over n, the probability of the event not occurring in the first tn minus 1 subintervals, and then the event occurring in the tnth subinterval, which is the last subinterval in this whole thing. And if you take this entire summation and you add up all of these different probabilities, this is going to give you a great estimation for the probability of the time to the first occurrence of the event being less than or equal to time t. But if we want to make this estimation, this approximation, if we want to make this exact, then we need to take the limit. This is actually going to be equal to the limit as n goes to infinity, as the number of our subintervals goes to infinity of this summation here. K is equal to 0 to tn minus 1 of 1 minus lambda over n, the probability of the event not occurring, the first k subintervals, times the probability of the event occurring in the k plus 1th subinterval. And so this is a perfectly valid representation of the cumulative distribution function for the exponential distribution. And so we've essentially accomplished our mission, but we can definitely clean this up. The sum here is pretty ugly, and we can get this in terms of a continuous function. The way we're going to do that is, first, we can factor out this lambda over n because it doesn't depend on this index of summation here. And so this is going to be equal to the limit as n goes to infinity, and then this lambda over n here just becomes some constant multiple being applied to all the terms of the sum. And so we can just pull it out, and I think I have the sum copied here. So we'll just multiply by the summation here. And then the reason we want to do that is that because then this becomes, this is just a geometric series. The first term of the series is 1, and then we have some rate value, and then we have that rate value squared, and then this pattern is going to proceed all the way to the last value here, which we'll just call r to the n. And if you haven't seen this before, we've done this like, I don't know, maybe 10 times on this channel before, but if you just multiply this series by r, and then we'll get r plus r squared plus plus r to the n plus 1, and then we can just take rs minus s, and what happens is all these terms cancel except for the 1 and the r to the n plus 1, and so we get r to the n plus 1 minus 1, and then we just factor out this s here, and we can solve for the summation, and this is just r to the n plus 1 minus 1 over 1 minus r, right? Yeah, no, r minus 1 over r minus 1. And so we can make this substitution here and turn this from what would go on to be an infinite summation, and we can turn it into a function, a continuous function. And so when we make the substitution using this fact from the geometric series, this is going to become equal to the limit as n goes to infinity of lambda over n. And then here we have r to the n plus 1. R in this case is 1 minus lambda over n to the n plus 1. And n here is the number of subintervals, or the number of terms in the series. And so this is tn minus 1. Tn minus 1 plus 1 is just tn. And then we're subtracting 1. And then we're dividing by r minus 1. And so our r here is 1 minus lambda over n. 1 minus lambda over n minus 1 is just negative lambda over n. And so quite nicely what's going to happen is this lambda over n is going to cancel with this one. And instead of having this negative in the denominator, this negative 1 in the denominator, I'm just going to multiply the top and bottom of this fraction by negative 1. And then this is going to quite neatly reduce down to the limit as n goes to infinity of 1 minus lambda over n to the tnth power. And from here, it really is just basic algebra. The limit of a constant, that's just equal to 1. And then we have minus the limit of this expression here, which I'm going to write in a slightly different way. This is the limit as n goes to infinity of 1 minus lambda over n to the nth power. I'm going to erase this whole thing to the tth power. And you probably need to do a little proof of this here. I'm not going to do it because this seems to make sense to me, but the idea that you can pull this limit inside of this exponent here, if I'm going to change this to 1 minus lambda over n to the n to the tth power, and then it would be the limit of that whole thing. And I'm essentially saying we can pull this limit in here because the exponent in the outer term here does not depend on the variable of the limit. You probably need to prove that, but I'm not going to. I'm going to trust that you are reasonably confident that this is true. And then what happens here, this is just the definition of e to the power of negative lambda. And so this whole thing is going to become 1 minus e to the negative lambda. And then we're exponentiating this to the power of t. Basic exponent rules. This would be 1 minus e to the negative lambda t. And so this is exactly equal to the probability of the amount of time being less than or equal to t. And given that this is equal to the probability of t being less than or equal to t, and we've defined this capital T to be an exponentially distributed random variable with rate parameter lambda, or in plain English, we've defined it to be the random variable that represents the amount of time to the first occurrence of an event, then this is just equal to, by definition of these random variables, this is the integral from the lower bound here, which in many cases is negative infinity, but in this case, since we're dealing with time, we can't have negative values, so this is going to go from 0 to t of the probability density function for an exponential distribution evaluated. We'll use some dummy variable here, x dx. And so if this is equal to 1 minus e to the negative lambda t, and we want to solve for this inner function here, just by the fundamental theorem of calculus, if we were to differentiate both sides here with respect to t, then what are we going to get here? Well, if we differentiate this with respect to t, from the fundamental theorem of calculus, that's just going to be the PDF evaluated at t. And so this will give us the function that we're looking for. This will give us a probability density function. And so in doing all this work to discover the cumulative distribution function here, this value here, this is the CDF, then we have immediately, actually, we have derived the probability density function as well. All we need to do is differentiate this with respect to t. And so if we differentiate with respect to t, this integral here, we'll just get the PDF evaluated at t, but this integral here is equal to the cumulative distribution function. And so if we differentiate this with respect to t, we'll get our probability density function, and this is just basic calculus, a chain rule and all that. We'll get lambda e to the negative lambda t. And so this is the probability density function for an exponential distribution. All right, now that we've got the probability density function and the cumulative distribution function, we've done all the hard work. We've completely characterized this distribution. Now let's see if we can find some properties of it. And so we'll start with the mean and the variance. I don't really like doing these integrals, but let's do it anyways. If we want the mean of an exponential distribution, we just need to integrate over all the values in its support. And remember, here we're talking about times. That's the story for this probability distribution, and so we can have negative values here. So this is going to be 0 anytime we have a negative value, so we might as well just integrate from 0 to positive infinity. Then we want to integrate our variable of integration multiplied by our probability density function with respect to our variable of integration here. And so this is going to tell us the mean of our probability distribution. Here I'll make a u substitution here. I'm going to let u be equal to t lambda, and then du here is just going to be equal to lambda dt. And if I want to solve for dt, dt will be equal to du over lambda. And also t here, t is going to be equal to u over lambda. And so essentially what's going to happen here is when I plug in this u over lambda for t here, we'll get 1 over lambda here, it'll cancel with this one. But then we're going to have an additional 1 over lambda here when I plug in this du over lambda for dt. And so what this is going to wind up looking like is we're going to have an integral from 0 to infinity, and then we'll have a constant of 1 over lambda, which I'm just going to pull out of the integral. And then what we'll be left with here is we're going to have u e to the negative u du. And then this integral, I'm pretty sure we need to do this with integration by parts. I hope there's an easier way to do this, but I don't know one. So I'm just going to let's do u is equal to u. So du here will just be equal to du. And then dv, I'm going to let this be e to the negative u du. And then v here is going to be equal to negative e to the negative u. And then by integration by parts, we'll have that this is going to be equal to 1 over lambda times, and then we have uv. And so that's just going to be u times negative e to the negative u. So this is negative u e to the negative u. Okay, got that. And then we're going to do minus the integral of v du. And so this is going to be negative e, negative u, and the du here is just du. This integral, I can do this one in my head. This is just going to be e to the negative u. When you differentiate, you'll get negative e to the negative u. So I'm just going to rewrite this as e to the negative u minus e to the negative u. And then what are we going to get here? This is just going to be... also, we need to evaluate this from 0 to infinity. And so I'm actually not going to bother reducing this any further. If I evaluate this at 0, what am I going to get? Well, here, this is going to go to 1, and so I'll have negative u minus 1. So this will be negative u... No, wait. If I evaluate this at 0, then this is going to go to 0, and then this is going to go to negative 1. Right? Yes. And so if I evaluate this at 0, it's going to be negative 1. And if I evaluate this at infinity, this is going to go to 0, and this is going to go to 0. And so evaluated at infinity, this is going to be equal to 0. And then we're going to minus it evaluated at 0, which is negative 1. And so this whole integral is just going to go to 0. Or go to 1. This integral is just going to evaluate to 1. Okay, I think I got that straight. And so if this goes to 1, then we'll get that the mean of this distribution is going to be equal to 1 over lambda. Okay. Alright, that integral was annoying. I'm still going to solve the variance, but instead of trying to get the second moment directly like I got the first moment here, and having to do integration by parts, I'm going to try and solve the moment generating function first, because I'm going to do that anyways, and there's a chance that if I solve for the moment generating function, it might be easier to differentiate than this function would be to integrate. And so we could use the moment generating function then to get the second moment. And then after we get the second moment, we could derive the variance from there using that and the first moment. And so the moment generating function here, if you recall, is just going to be e, or the moment generating function will just be the expected value of e to the power of s times our random variable, which in this case I was using t because it's representative of time. This is just by the law of the unconscious statistician equal to the integral over all the values of the support of e to the s times our dummy variable. And then we're going to multiply by the probability density function. There's a lambda here, but I'm going to pull that lambda out of the integral because it's just a constant. And so we'll be multiplying by e to the negative lambda t dt. And then here, this is just laws of exponents. It's just lambda times the integral from 0 to infinity of e to the, and then in this case it would be t times s minus lambda. But I'm going to pull that negative one out, so I get negative t. And then instead of s minus lambda, it'll be lambda minus s, since I'm pulling out a negative 1. And the reason I want to do that is because I'm going to make a u substitution, where u is equal to t times lambda minus s. And then du here is going to be equal to, we'd get lambda minus s dt. And if we wanted to solve for dt, we'd just do du over lambda minus s. And so now this integral is going to reduce to lambda times the integral from 0 to infinity of e to the negative, then what do we get here? We get negative u. And if I wanted to plug in this du, or if I wanted to plug in du here, I'd have to solve for dt. That's du over that expression there. So this is going to be du, and then we're dividing this whole thing by lambda minus s. But since lambda minus s is a constant, and neither s nor lambda appear in they're not the variable of integration, we can just pull that out. And so we'll get lambda over lambda minus s. And now this integral is very easy. This is just lambda over lambda s, and then we're multiplying by negative e to the negative u, evaluated at 0 and infinity. Evaluated at infinity, this is going to go to 0. Evaluated at 0, we're going to get negative 1. This is going to be 0 minus negative 1, so this whole thing is going to go to 1. And we'll just be left with, this should be lambda times lambda over lambda minus s. But we'll just be left with this here. And so our moment generating function for our distribution here is just going to be lambda over lambda minus s. All right, so now that we have this moment generating function, we can just differentiate this with respect to s, and that's just the chain rule. And so our first moment, we should differentiate with respect to s, our moment generating function here. This, like I said, this is just the chain rule. We can pull out the constant of lambda, and then this is lambda times the derivative with respect to s of 1 over lambda minus s. And this is just s to the power of negative 1, essentially, but this is the chain rule. We have a function here, lambda minus s, so this is just, you would have g of x, or you would have f of x is equal to 1 over x, and then you would have g of x is equal to lambda minus x, and this would just be f of g of x. And so this derivative here would just be the derivative of f evaluated at g of x. And so what is that? That's just going to be negative 1, right? Lambda times negative 1 over lambda minus s squared, but then we need to multiply by the derivative of the inside here, which is just negative 1. And so if we multiply by negative 1, what are we going to get? We'll get lambda over lambda minus s squared. And if we were to evaluate this at 0, what would happen? We'd get lambda minus 0 squared, and so we'd have lambda over lambda squared. And so evaluated at 0, this becomes equal to 1 over lambda, which is what we get for our first moment here. So this is a good indication that our moment generating function here is correct. But if we wanted to actually solve for the second moment here, we'd have to differentiate one more time. So this is going to be no problem. It's just lambda times the derivative with respect to s. But in this case, it's 1 over lambda minus s squared. This is just once more doing the exact same thing. So this is here, f of x would be 1 over x squared. G of x would be lambda minus x. And so this is just the chain rule. So we get lambda, and then the derivative of the outside function here, this is going to be times negative 2 over lambda minus s to the third power. Then we multiply by the derivative of the inside, which is once again negative 1. And so we get for our second moment, the expected value of t squared here, our second moment. This is going to be equal to, let's see, the negatives would cancel, and we get 2 lambda, and then we'd evaluate this at s is equal to 0. So we have 2 lambda in the numerator, and then we're evaluating at s is equal to 0, so this becomes lambda cubed, and we get 2 over lambda squared. That's our second moment. So our variance, this is going to be equal to our second moment here minus our first moment squared. And our second moment is 2 over lambda squared, and our first moment squared is going to be 1 over lambda squared. And so 2 over lambda squared minus 1 over lambda squared, this is just equal to 1 over lambda squared. So this is our variance of an exponential distribution. And so that was derivation for the variance, the moment generating function, and the mean of the exponential distribution, as well as the probability density function and the cumulative distribution function. And you might think that with that, there's nothing more to talk about this distribution. We got the mean, we got the variance, we got the moment generating function. But there actually is one more thing that's unique to the exponential distribution. And to illustrate it, I have this little question here. I like to call this the curse of the person who's waiting for a job interview call. I don't actually like to call it that. I just think this is the example I thought of. So imagine we're anticipating a call from 2 to 2:30 regarding a job interview. Reasonably, you decide to expect that they're going to call you about halfway through the time block. It's just natural to assume. So you're expecting this call to occur at 2:15 p.m. You're expecting to have to wait 15 minutes. So starting at 2 p.m., you wait 15 minutes, but you're starting to get antsy because this is when you thought you were going to get the call. And so you decide to occupy yourself by computing the probability of having to wait more than 10 more minutes, given that 15 minutes have already passed. You're thinking, how bad could it be? Am I going to have to wait more than 10 more minutes? And you're going to do this, you're going to compute this probability by assuming that that t, which is what you call the time to the first instance of a phone call, is going to follow an exponential distribution. So we're asked to explain our results with respect to this question. And so mathematically what we have here is we're expecting to have to wait 15 minutes, and we're modeling this as an exponential distribution. And so the expected value of t here, the time to the first occurrence of the event, this is going to be 15 minutes. 15 minutes. And so what does this tell us? In an exponential distribution, we know that the expected value is going to be 1 over the rate parameter lambda. And so this tells us that our rate parameter is just going to be 1 over the expected value, and so this is going to be 1 over 15. And so now we have a probability density function with which we can compute these probabilities, and a cumulative density function. And I think another little fact to point out here, since we're interested in what the probability is of having to wait more than 10 more minutes. And so we have their cumulative distribution function, which tells us the probability of having to wait less than some amount. We know that this is equal to 1 minus e to the negative lambda t. But what about the probability of having to wait more than some amount? Well, in this case, this is easy. This is just 1 minus the cumulative distribution function. And 1 minus this here, those 1s will cancel, and this negative will become positive. So this is just e to the negative lambda t. It's going to help us with this problem here. And so we figured out what the rate parameter is, which means we have a probability density function to model this situation. And now we've already waited 15 minutes, and we want to compute the probability of having to wait more than 10 more minutes. And so what does that mean? That's the probability of having to wait 10 more than 15 minutes is 25. So that's the probability of t being greater than 25, given that t is already greater than 15. And let's stop and try to make some predictions here before we actually move forward with computing this mathematically. If you were just starting and you thought about what your probability was of having to wait at least 10 minutes or more than 10 minutes, you would expect that that'd be a reasonable probability, right? You're expecting that you're going to have to wait 15 minutes, so if they call you after 10 minutes or less than that, something like that, then you would be pleasantly surprised. But if you've already waited 15 more minutes, you'll probably start to expect that the probability of having to wait more than 10 more minutes is going to be less than if you were to start at the beginning. If you're starting at the beginning, then having to wait more than 10 minutes, that's a reasonable amount to wait. But if you've already waited 15 minutes, you're going to expect that your probability of having to wait more than 10 more minutes, that's going to be smaller than the probability of having to wait more than 10 minutes at the beginning. That I believe would be a reasonable expectation. So probably you're optimistically computing this probability here as you're trying to figure out how much longer am I going to have to wait before this job interview people call me. But if you actually compute this, what is this probability equal to? Well, if you use Bayes' rule, this is just the probability of both of these events happening. So this is the probability of the time being greater than 25 and the time being greater than 15, divided by the probability that we're conditioning on. And so that's the probability of the time being greater than 15. But here, if you notice in this numerator, the probability of t being greater than 25 and t being greater than 15, this is exactly the same as the probability of t being greater than 25, because this entire statement is only true if both of these statements are true. And this statement, if this statement is true, then this statement's always true. And so we don't even need, we could just completely ignore this. It's actually extraneous information. And then this becomes equal to the probability of t being greater than 25 divided by the probability of the time having to wait being greater than 15. And so what happens if we compute this probability? Well, we can use these values here. What are we going to get? We'll get e to the negative, and we have our lambda here. I'm not going to use it. I'm just going to use lambda 25. And then we're going to divide by e to the negative lambda 15. And so now by our properties of exponents, we can just subtract this exponent from this one. And that's the same as adding lambda 15. And so what are we going to get? We're going to get e to the negative lambda 10. And this is exactly equivalent to the probability of t being greater than 10, the probability of having to wait more than 10 minutes, if we just started at 0. And so this property is called the memoryless property. This is the memoryless, it's kind of a hard way to say, memoryless property. And this tells us that it doesn't really matter how long we waited. That doesn't do anything for us. Given that we've waited 15 minutes, the probability of having to wait more than 10 more minutes is exactly the same as having to wait as the probability of having to wait more than 10 minutes from the beginning. And so this tells us that this distribution is essentially going to forget the past, and every single moment it's like you're starting from new. And no matter how long you wait, the probability of having to wait a more minutes is exactly the same as having to wait more than a minutes if you were to start from the beginning. So this is the memoryless property of the exponential distribution, and a little derivation of where this property comes from. And an interesting fact about the exponential distribution is that this is actually the only continuous probability distribution that exhibits this property. A proof of that requires functional equations. It's not that complicated, but it's just not something I want to cover in this video that's gotten so long. And so this is just a proof that the exponential distribution does exhibit the memoryless property. Proof by example here. You can replace these numbers with whatever variable you want. I just want to give a little example to illustrate what exactly is meant by this memoryless property. And I think that's going to do it for this video. That covers the memoryless property, the variance, the mean, the moment generating function, the probability density function, and the cumulative distribution function for the exponential distribution. I wanted to use this video as a chance to talk about continuous random variables and what they actually are, but I think this video has gotten too long already, so I'm going to do that at a different point. Exponential distribution is a particular case of a family of distributions called the gamma distribution, or I guess gamma distributions. And so the next video will probably consist of a derivation of the probability density function for this entire family of distributions, those gamma distributions. And then after that, that's going to open the door to many different distributions. So at this point in the course, we're just going to be rapid fire going through all the different distributions that you're going to need in statistics. These are all very important, so it's worth learning at least the formulas that they use. You probably won't need those on an everyday basis, but it's worth noting at least what these distributions are meant to model. I'm going to try and go through and show where all of the formulas for all of these distributions come from. That's my goal with this series. So hopefully that's at least interesting. Thank you guys for watching. I'll see you in the next one.